So what is a complex number? Let's look first at the numbers that you may well be familiar with, the good old natural numbers, counting numbers, 1, 2, 3, and so on. You also should be familiar with the integers, positive and negative counting numbers, including 0. So -2, -1, 0, 1, 2, and goes on. And also you should be familiar with the rational numbers, which can best be described as the ratio of a couple of integers, where the bottom one is not 0. So m is an integer, and to avoid the 0 we could say n's just a natural number. So we've basically got the integers here, and also halves, thirds, quarters, and any fraction of an integer in this rational set. And finally, the good old workhorse. Most of your mathematics, in fact probably all of the mathematics you've ever done, has been in the set of real numbers. Very difficult to list these. What we could say is that they can be represented by decimals, whether they terminate or don't, stop or continue. So terminating or non-terminating. So any real number could be written as a decimal. Another way to think about the real numbers, a very useful way, is that they can be represented by all the points on this number line. That's why it's called the real number line. So we pick any real number, there's the set of real numbers, take any real number and it will correspond to a point on this number line, and vice versa. Any point in this number line will correspond to a real number. But there's uncountably infinite number of real numbers. So why on earth, given the rich structure and the immense stretch and use of these, the facility that's available is just extraordinary, why on earth would we need something else beyond that? Well, let's just try and solve one equation. And the equation I want you to try and solve is x squared minus 2x plus 5 equals 0. So why don't you stop the tape and try this question. Just try to solve that equation. Okay, how did you get on? You should first of all have recognized this as a quadratic equation, and therefore your thought processes, I hope, will be towards the use of the quadratic formula, minus b plus or minus the square root of b squared minus 4ac all over 2a. And the a's and the b's and c's, recall, are coming from the coefficients of the x squared and x term, or the constant term. So in this case, a is 1, b is -2, and c is 5. So we can launch straight into calculating the solutions to this equation. Minus b would be 2, plus or minus the square root of b squared, -2 squared is 4, minus 4 times a is 1 and c is 5, all over 2a, twice 1 is 2. So we get 2 plus or minus, and this turns out to be 4 minus 20, which is -16. And now, normally what would then happen is you'd say that there is no real solution, or there are no real solutions. And the reason being that the square root of -16, if you hunt among all the real numbers, that's represented by points in this line, if you hunt for a number which, when you square it, you get -16, I don't think you'll find one. For instance, if it was a positive number, squaring a positive number gives you a positive answer. You won't get negative 16. And if you take a negative number, at some point to the left of the point representing 0, if you take a negative real number and square it, you get a positive real number, so we can't get negative 16. So this cannot be a positive or a negative real number. The only other type of real number is 0. It's neither positive nor negative, and certainly 0 squared does not give us negative 16. So we're stumped. Out of all these numbers, this rich seam of numbers along here, there is not a single number whose square is negative 16. So that would be where we would leave the story previously. However, let's go slightly further with this. Let's do a little bit of work on this, just using our normal rules of algebra. We know that negative 16 is 16 times negative 1. And we know there is a result which says the square root of the product of two numbers is the square root of each of them multiplied together. Square root of ab is square root of a times square root of b. Now, assuming that we can do this with a strange entity like the square root of minus 1, then this is what we end up with. So let's just move forward with this slightly. We know that the square root of 16 is 4. The square root of negative 1 is, as we know, not a real number. And we have to halve 2 plus 4 times that not real number. So everything in the top line gets divided by 2. 2 into 2 is 1. 2 into 4 is 2. So we get twice, 1 plus or minus twice whatever the square root of negative 1 is, not a real number. So we have ended up with two solutions. 1 plus twice the square root of minus 1, and 1 minus twice the square root of minus 1. And neither of these, whatever they are on this real number line. So we're faced with the dilemma of, yes, we can go further with this, provided we accept this entity, whatever it is. Let's just, for the sake of argument, call it I. We'll give it a symbol, I. Now, because it's supposed to be the square root of negative 1, I would therefore have the property that when we square it, we will get minus 1. And notice I'm going to assume that this thing behaves as real numbers do. All the properties of real numbers under addition and multiplication, subtraction, all the rest of this, I'll assume the same properties are obeyed by this thing. It has an additional property that when you square it, you get negative 1. So let's just write down what we've got so far. 1 plus twice I, or 1 minus twice I, where I is something, certainly not a real number, that has the property that when you square it, you get negative 1. Now, you are looking at, let me just wipe this line out, you are looking at two complex numbers. This is a complex number. So we're looking at a real number plus another real number times a symbol I, whose properties are all those of the real numbers apart, well, not apart, in addition to this wonderful property that when you square it, you get negative 1. Here's another one, a minus bi. We could have a negative in there, but basically, I suppose if all the rules of real numbers behave themselves, then it would just mean that b in this case is negative 2 and a is 1. So here we have a typical complex number. And this is called the real part. And this number here, the b, is called the imaginary part. Let's just wipe out what we have here and recap that a complex number is a number of the form a plus bi, where a and b are both members of the set of real numbers. Now, the equation that I gave you originally, x squared minus 2x plus 5 equals 0, should therefore be satisfied by two values of x, 1 plus 2i and 1 minus 2i. So these complex numbers should satisfy this equation. Now, shortly we'll have a look and see if that's true or not. But one thing to note is that usually in maths, when we write x and y as variables, we inevitably mean that they're in the set of real numbers. So there is a convention that says if we use, for instance, z and w, then we are in the set of complex numbers. So z is a complex number if it's written as a plus b I, where I, as we know, has this property I squared equals negative 1. This is sometimes called the Cartesian form of the complex number. Cartesian form. And the whole set of complex numbers use a C. I'm using double lines here because in printed text this is bold font, as is R for real numbers, bold font. Very difficult to write in bold font, so sometimes you tend just to use a double line to show that. But bold font, capital C, is the set of Z where Z is of the form a plus ib, where a is a real number and b is a real number. So it's that set of objects, if you like. All the normal rules of real number addition, multiplication, subtraction, division, etc. are supposed to hold. Whenever you come across an I squared, you get a negative 1. Now, before we move on to checking whether these two complex numbers do satisfy this equation, which will be a bit of fun, there's one thing we should add, that the real part of a complex number Z, maybe I shouldn't use the double line there, real part of Z is A, and the imaginary part of Z is B. So notice now that the real part is a real number, the imaginary part is a real number. So A is the real part of the complex number Z, B is the imaginary part of this complex number Z. Now, I would like you to try now a question. So stop the video and try this question. So the question is, I'm going to give you a list of complex numbers. Here they are. 2 plus 3i, root 3 plus I pi, 6, 4i, 1 minus I, 0, and negative 2 minus 3i. So your task is to work out what the real part of z is and what the imaginary part of z is. So stop the tape now and try that. So how did you get on? Real part of z is 2. Imaginary part of z is 3. The real part of z is root 3. The imaginary part is pi. The real part is 6. The imaginary part is 0. Notice here we can write 6 as 6 plus 0 times I. So real part 6, imaginary part is 0. And this highlights the fact that the real numbers can be retrieved from a complex number by saying its imaginary part is 0. That gives you x. The set of real numbers basically are a subset of the set of complex numbers. This complex number, the real part is 0. The imaginary part is 4. Now, a number in this case is called purely imaginary, the real part being 0. Likewise, this is called purely real. The imaginary part is 0. So if the real part's 0, you've got a purely imaginary number, and if the imaginary part is 0, then you've got a purely real number. If z is 1 minus I, the real part is 1, and the imaginary part is minus 1, negative 1. The number 0 as a complex number has real part 0 and imaginary part 0. In this case, think of 0 plus 0 times I. And finally, negative 2 minus 3i, real part is negative 2 and the imaginary part is negative 3. So how did you get on? Did you get these right or what? You can certainly review it if you want. I'm now going to move on and we're going to look at the original equation and see whether 1 plus 2i satisfies the equation we started with, which is z squared minus 2z plus 5. And remember, the reason I'm using z now is because we're admitting the possibility that this equation might have a complex valued solution to it, not just real numbers, in which case I would have used x. So we need to square 1 plus 2i. Now remember, these expressions, these complex numbers, behave as real numbers would, apart from the fact that when we come across an I squared, I times I, we get a negative 1. So I'm going to use the expansion of two brackets, firsts, outsides, lasts. Firsts give me 1. The outside 2 give me 1 times 2i. The inside 2 terms give me 2i times 1. And the lasts, 2i times 2i. Well, that requires a little bit of thought. Well, 2 times 2 is 4, and I times I is I squared. I squared, we know, is negative 1. So we get negative 4 for multiplying these lasts together. So we've ended up with 1 minus 4 negative 3 as the real part of z squared, and 2i plus 2i is 4i. 4 being the imaginary part. So we've got negative 3 plus 4i, one complex number, z squared. Minus 2z, we can have a look at that. If the rules of normal real number arithmetic hold, then we've got a distributive law, negative 2 times 1, getting rid of the brackets law, negative 2 times 1, and negative 2 times 2i would be negative 4i. So that's what we'd get for that bit. So let's check now that we've got all these results, what the value of z squared minus 2z plus 5 is. Z squared we know is the complex number negative 3 plus 4i. Minus 2z is the complex number minus 2 minus 4i. And we have to add 5 to that. So let's look at the real part of this. Negative 3 plus negative 2 is negative 5, plus 5 is 0. And the imaginary part, 4i minus 4i, 0i. So basically 0 plus 0i we write as the number 0. In other words, 1 plus 2i does satisfy that equation. So a question for you. Look at the equation z squared, move this down a bit, z squared minus 2z plus 5 equals 0, and show that the complex number z equals 1 minus 2i satisfies this equation. In other words, it's a root of that equation. So stop the video, try that now. Okay, how did you get on? Let's try it in a winner. So 1 minus 2i z squared minus, we're substituting the complex number 1 minus 2i for z. So that's what we're trying to do. 1 minus 2i, perhaps it's easier if we look at these two. 1 minus 2i times 1 minus 2i. So first term is 1. Outside minus 2i, inside minus another 2i, so that's minus 4i. And then the more complicated bit of it, negative 2i times negative 2i. Well, negative times negative gives me positive. 2i times 2i is 4i squared. So we get positive 4i squared. However, I squared is negative 1. 4 times negative 1 is negative 4. Getting rid of brackets, minus 2 plus 4i. And then we've got 5 to add. So real part, 1 minus 4, that's minus 3, minus another 2 is minus 5, plus 5 is 0. And minus 4i, the imaginary part, minus imaginary contribution to this number, minus 4i plus 4i is 0. So 0 plus 0i, just written as 0. And certainly 1 minus 2i is also a solution of that equation. So one last question for yourself to try. Solve z squared plus 4z plus 5 equals 0. Use the quadratic formula to solve that, and then show that the roots you get, the solutions to this you get, do actually satisfy this equation. Try that now. Okay, let's see how you got on with that. So the first thing would be to use quadratic formula, minus b, negative 4, plus or minus square root of 16, minus 4 times 1 times 5. That's minus 20. All over 2 ones are 2. So we get negative 4 plus or minus the square root of negative 4. All over 2. And we can write negative 4 square root as, we'll do this splitting into factors. Take the square root of each part. So we would get 2 times I. So it's plus or minus 2i, and that divided by 2. So the final two solutions are negative 2 plus or minus I. So let's just write that out. Z is negative 2 plus I, or Z is negative 2 minus I. And to check whether negative 2 plus I is a solution of that, we'll take negative 2 plus I and square it, add 4 times negative 2 plus I, and add 5. So negative 2 plus I squared will be 4 minus 4i, and the last terms will give us minus 1, check that, minus 8 plus 4i plus 5. And when I check that, 4 minus 1 is negative 3, minus 8 is negative 11, plus 5 is negative, oh, I'm lost here. 4 minus 1, that's 3, minus 8 is negative 5 plus 5. Sorry, that's 0. Lost the plot there. Negative 4i plus 4i is 0 also. So that certainly does satisfy that equation. And we can also do a similar thing with negative 2 minus I squared when we put that in. Let's just check that that works. So the firsts will give us negative 2 times negative 2 is positive 4, and the insides and outsides will give us plus 2i plus another 2i, so this time it's plus 4i. And the last, negative I times negative I, is positive I squared, which is negative 1. And we get negative 8, however, not a plus 4i, we get a minus 4i this time. So everything's the same as before, except the imaginary terms are the negative of what we previously had. So 4 minus 1 is 3 minus 8 is minus 5 plus 5, 0, and 4i minus 4i is 0 also. So they do, these two complex numbers do satisfy this equation. Factors.